So you can say, well, this is good, but can we improve even beyond this? Well, actually, yes. Now, here is like what we will do. Now, let's see that, we can, what we will do is we will be doing this multiplication by blocking and splitting this into sub matrices. So this is our, again, matrix multiplication. And this we are talking about IJK loop, except that instead of CIJ, I'm just using these indexes, which is, nothing fancy. Now, what I will note is the following. Let's do this cache miss analysis. And in this case, let's say that the matrix elements are doubles, 8 bytes, okay? And if our cache block size is 64 bytes, it can store then 8 doubles in this case. And let's assume that the cache size is much, much smaller than n, okay, which is the size of our matrix. Okay. Now let's look at our first iteration. In the first iteration, you can see that I am accessing basically this is my A and this is my B, right? Okay. In here, how many misses do I have? And I have n elements in here. So in here you can see that due to this, I can store 8 doubles at a time in here. So when I bring them into my main memory, then I will have a miss here, but then you will have a hit, okay? So in total, if I have basically n elements, I will have n over 8 misses due to access A. Now what about B? In the case of B, whenever I try to access this, then this whole basically 8 doubles will be brought into memory. It will be a mess, but then in the next iteration, what I will do is now I will be accessing the second one, and again it will be a mess. So in the for when I'm accessing B, then I will have n misses due to B. So in total, I will have 9n divided by 8 misses, and in a single iteration. And at the end of the first iteration, then what will I have in my cache? In my cache, I will have this 8 bytes here, and then I will have this 8 by 8 elements in the cache. Now, what happens in the second iteration? So in the second iteration, now, I'm again multiplying this. Now, this one has moved one more. And in here, again, when I'm accessing A, okay, I will again have n over 8 misses because, remember, at the end of this was in the left in the cache, but the one that I will be accessing here now here, this one, it will be a miss. Okay, it's interesting. So if I go like this, then this one will be removed from my memory, from my cache, okay? And then hence, as a result, this will be due, this is A, and this is B, okay, due to A. And what about in the case of B? Well, when I'm multiplying this, again, I will be accessing this, okay? But this whole basically line will be, the data block will be brought into memory, okay? And the fact that this was in the main memory will not benefit me. Okay? As you move down, actually, this one will disappear. Again, we will have, n misses due to, again, B. So I will have 9n divided by over 8 misses. So now, for this iteration, remember that, in this case, I will have to compute, n squared, okay, C elements, right? So 9n over 8 times n squared, okay, this is the number of elements in C. That hence, that means that I am looking at a total number of 9 over 8 n cubed misses in this case, right? So can I reduce this? Now, for this, we should, again, you're taking linear algebra, right? And in that case, if I have a C, A, and B, one of the tricks that they've shown you is if you have a matrix like this, you can actually split this into sub-matrices. And with the sub-matrices, then you can actually, if I'm computing this, That means that you multiply this one, B here, with this one. And hence, I can write this like the C11, like these are all matrices. Okay, if the C is, for example, 8 by 8, and this is a 4 by 4 matrix. So I can say that the C11, which is a matrix, is actually A11 times B11. So you multiply this with that, plus A12 times A12 times B21. Yes, exactly. So this is matrix multiplication, and plus. Okay. So this I can compute C11 here. And C12, again, you write like this. So this is essential. I'm splitting this matrix into sub-matrices, okay? And now I'm doing this much smaller scale matrix multiplications here, okay? So this is, again, mathematical. So what I can do is now I can do this blocked matrix multiplication. You can see that the first for loop here, this is our regular matrix multiplication. But in here, I do the mini matrix multiplications, which is again a triple for loop here. So this is the part where I am doing these multiplications. So in this case, you can see that, like, I have these multiplications here that we divide them into these, in this case, the indexes are I1, J1, K1, okay? You split into these small blocks, okay, of size, say, B by B, okay? And then you just do these block multiplications and then add them in. So let's do this cache miss analysis when we block things, okay? Again, we assume that, the cache block contains 8 doubles, okay? The cache size is much smaller than n. And here we have a new one, which is, we say that the 3 blocks fit into the cache. So remember that the block size was, B was this block size. So here's let's look at our first block iteration. In the first block iteration, remember that, I have this is my block here, and then this is the block from and this is A and C. Let me just write here. This is A and this is B. But don't get confused this B with this B. Okay, you can see that that's okay. This B is the block size. This B is the C equals A times B. Okay, don't get confused. So now what do we do? Like when I'm we can see that for each of them, like in here, like this is updated only once. So I'm just focusing on A and B here. So when I'm accessing this one, okay, here, then how many misses will I have for each block? Well, in this case, you can see that, like, since my cache block contains 8 doubles, it will be essentially, b squared divided by 8 for each block, because I will have b squared items here. And if you divide it by 8, then that will be the number of misses when I'm accessing this block. And the same goes here, okay, for b as well. So in total, when I'm doing this multiplication, I will have n over b. Well, n is the size of the big matrix, and b is the block size, okay? So I will have n over b blocks here, and n over b blocks here. So I will have 2n over b blocks in total from A and B. And for each of the blocks, then I will have b squared divided by 8 misses. And as a result, if I'm neglecting matrix C, then I will have nb over 4 misses, okay, to compute basically C block here. And at the end of the first iteration, then I will have some amount of basically this A, and this portion from P will be left in the main memory. Okay. Now we can also see that, like, when I'm doing this, when I make this condition that 3b squared is less than or equal to C, what I'm essentially saying is, when I'm multiplying this one with this and updating it into this one, these 3 should be all fit into my cache. Okay. That's basically the idea. If I don't fit into my cache, then I will have basically I have to go one more level, which will complicate. Now, what happens in the second block? Okay, well, in the second block, remember that I'm again taking the first row, but I'm talking about the second column of the second matrix. Okay, and again, it will be say the same thing. So I have n over b blocks here. I have n over b blocks. It will be 2n over b blocks, and I will have b squared divided by 8 misses. So I will have nb over 4 basically misses in second iteration as well. So the total number of misses is that to complete each block here, each block in C, I will have to have n times b over 4 misses. And how many blocks do I have in my, this is essentially, so this is the number of blocks, okay? In this case, block is kind of mini matrices. Okay, don't confuse these blocks with the data block of the cache in matrix C. So it means that I multiply this with n over b squared, and the result is n cubed over 4b. So with this, you can see that if I did no blocking, then the number of misses that I would have was 9 over 8 n cubed. And if I do blocking, it will be essentially n cubed over 4 times b. Now, what does this correspond to? Well, let's take this, for example, our L1 cache in the I7. In this case, the cache size for L1 was 32 kilobytes. Okay, this is just an example, right? 32 kilobytes is 2 to the power 15 bytes. Now we say that we want to make sure that the 3 mini matrices should fit into my basically cache. So my condition is, I want to basically take the largest possible block size, okay, but make sure that basically 3 times b squared is less than c. So I want to make sure that 3 times b squared should be less than 2 to the power 15 bytes, okay? And this means that the b squared should be less than 2 to the power 15 divided by 3. Let's make this 4, just roughly. So b squared should be less than 2 to the power 13. And one thing is that I can decide b as 2 to the power 6, okay? Which is what? This is approximately, this is 164, okay? So what this means is, like in here, with no blocking, I will have 9 over 8 n cubed misses, whereas here I will have 1 over 256 n cubed misses, okay? So you can see that like this one has 250 times less misses, okay, in terms of matrix multiplication. And so when you do this, the speed up that you will get will be huge, and it will be a huge dramatic difference, okay? And this is like, you can see that like this, we can do this because in the matrix multiplication we have inherent temporal locality, okay? The input based data is 3 times n squared. You have 3 n square sized items, whereas the computation is 2 times n cubed, and every element is used in order n times, but you have to write the program properly.